So we're looking at the incline plane worksheet. There are 5 problems that we're going to be looking at today, and we're going to want to do free body diagrams for each of these to get you set up on your problem solving. So the first one, we have a 30.0 degree angle. All right, class, I want you to tell me, give me a force that should be on this diagram here. Okay, that should be the one that we draw in first, and that should be straight down. So we have the weight of the object. What else do we have? FD. Okay. We can break this into a triangle, a right triangle. I'm going to just kind of draw that in here fairly lightly. And we can break this into components. And this angle here we've talked about is congruent to this angle here. And we have this weight, we have part of the weight that's pushing into the surface, and we have part of the weight that's then causing it to go down the incline. Essentially, we could draw them as vectors that look like this. And some teachers actually label them like this, and they call this W weight X and weight Y. I don't like that notation just because of it's not really in the X direction and Y direction. I guess if you were to flip it like that, then you'd have it. But some teachers will do that, and that's how they label them. But what is essentially weight X? What have we been calling that component? We've been calling that FD. And weight Y, because this is actually the only part of the weight that's pushing against the surface pushes back on the block. And that's what we're calling Fn. So Fn is actually equal to that component of the weight. So instead of showing it like this, I just show it like this instead, where you have your weight down. This is your normal force, and this is your force down the ramp. Okay? But that's where those come from. They come from this knowledge here that we can break this vector into its components that are at right angles and parallel to the ramp to help us look at the motion of that block. Which way is this block moving? So it's sliding down the ramp, and it tells us some things about its slide. It says it's sliding with a constant velocity. So that means what? It has a net force of 0, so the acceleration is 0. And the net force on the block is 0. So that means the forces down the ramp are equal to the forces up the ramp. So right now I have a force down the ramp. I also need to show a force up the ramp, and that would be called what? FK, that's kinetic friction. And I should show that those two vectors have the same magnitude. Okay? This is what I'm looking for if I ask you for a free body diagram. And then I can set up an equation that relates these things. And we just said it, that this is 0. So the forces down the ramp are equal to the forces that are up the ramp. And from there, I should be able to solve everything else. I should know how to solve for the weight. It's just mass times gravitational acceleration. I should know how to solve for FD and Fn now, because this is a right triangle. This is the hypotenuse. What trig function am I going to use to solve for FD? FD, folks. It's the opposite side, so I'm going to be using the sine. So it's the sine of the weight. So it's weight sine theta for FD. Again, I'll just do a quick review of where this comes from. If I know the opposite side in the hypotenuse, the sine of theta is equal to the opposite over the hypotenuse. That's where it comes from. And then if I'm solving for FD, it's just weight sine theta. And then finally, Fn is what? If FD is weight sine theta, then Fn is weight cosine theta. So from that information, you should be able to solve for FD, Fn, and then once you know FD, you know Fk, and then what's the final thing we're solving for? Mu k, which is just Fk over Fn. And we'll have known those because there's FD, there's Fn, You can actually do substitution and see that this is equal to the tangent of that angle for the first one. Any questions on number 1? You guys can finish that up on your own. Again, I'm just going to kind of go through the setup on each of these. All right, number 2, we're going to be a little bit quicker on number 2 here as we set it up. It's very similar. Same thing. Same forces. We've got weight, which is down. We have the normal force, which is pushing up on it. We have the force causing it to move down the ramp. What's the block doing this time? It's accelerating down the ramp. So what does that tell us about friction? If it's accelerating down the ramp now, friction's got to be less than FD. So I'm going to just put a little small frictional force in there. And now, instead of the net force being 0, the net force is going to be equal to the forces in the direction of motion minus the forces that are opposing motion. And this is no longer 0. Need any more help getting that started? This is equal to mass times acceleration. FD we can find, FK we can find, just like we did in the first one. Those don't change. But now we know in acceleration we have the mass of the block. Set it all up, solve for FK, solve for mu K. Good? Number 3. This is where we start getting into a little bit more difficult work. So I'm going to spend some time on number 3 on the first part and then show you how it's pretty similar on 4 and 5 as well. So here we have a block that's on connected to a string on a pulley with another mass. Again, let's draw in our forces. What forces do we know on block 1 over here? We know it's weight. What else can we find? Fn, Fd, what else? Okay, which way is kinetic friction? Why is it down the ramp? Yeah, it says the block slides up the ramp, so kinetic friction is going to be down the ramp. And what else is pulling on this? Tension in the rope. Those are all the forces that are acting on block 1. Block 2, what do we have? Weight and tension. So let's write equations for both 1 and 2. So for block 1, the net force is equal to what? The forces in the direction of motion minus the forces opposing motion. Which way is it moving? It's moving up the ramp, so what is the force in the direction of motion? Tension. Minus the forces that are opposing motion. In this case, Fk and Fd. We subtract both. Let's go to the second block. Which direction is it moving? It's moving downward. So the net force for this one is equal to the weight, which is the force in the direction of motion, minus tension. And how is this system moving? It says that this is moving with a constant velocity in the problem. So if that is true, that means the acceleration is 0 and the net force on these is 0. So what is tension equal to? Okay. In this equation, it's equal to Fk plus Fd. And in this equation, we'll put 2's on these so we know. And here the tension is equal to weight 2. And remember, we've talked about this, that the tension in the rope is constant throughout the rope. So the T here is equal to the T here. And because of that, we can then set these two tensions equal to each other. And that's where we get our equation from. Weight 2 is equal to Fk plus Fd. And now we can just solve for these individual pieces. We can solve for Fd pretty easily. It's going to be the sine of this weight, or sine of theta times the weight. Fk is mu k Fn, and it gives us a coefficient of kinetic friction. So that's pretty easy. We can solve for Fn. And then weight is just mass times gravitational acceleration. And we are trying to find the mass of block 2. That's what we're looking for. So this would be mass 2 times g equals Fk plus Fd. So mass 2 is equal to this divided by g. That's how we should end up. And again, you can solve for these items off to the side and then plug them in. Questions on part A of number 3. How is B different? It's sliding down. So look, here's the only change. It is now sliding down the ramp with a constant velocity. So which way is friction? Up the ramp. So look here, I'm going to erase friction from this side, and I'm putting friction over here. So that just changes my equations. So I'm going to rewrite my equations here for sliding down the ramp. So let's do it. The net force is equal to the forces in the direction of motion. Which way is it moving? Down the ramp. So what force is in the direction of motion for this block? Fd. Minus what forces are opposing motion? Friction and tension. Let's look over here on the second one. What's the direction of this block? Which way is it moving? This is sliding down the ramp. The block is moving up. So this one is going to be tension minus weight 2. How is it sliding? Constant velocity. That means the net force is 0. So if I were solving for t, then this is 0. T is equal to Fd minus Fk. What is tension equal to over here if this is 0? Still equal to weight 2. So here are my two new equations for it sliding down the ramp. Can I set them equal to each other? Absolutely. So now it's weight 2 is equal to Fd minus Fk. So it's going to be very similar to this. The only difference is we put a negative sign because friction changed directions on that. See how it's very similar? Again, here it's a positive. It's in the same direction as Fd. Here it's in an opposite direction of Fd. Questions on 3? That should hopefully get you started and get those taken care of. All right, let's look at 4. What's the difference in number 4? What's going on with our object? Sliding up the ramp, right? Same thing, same setup. This then would be the weight 2. Tension is up here, tension here, weight 1, normal force, Fd. Which way is friction? If it's sliding up, friction is down the ramp. Can you write your equations? Let's see if you can do it. Pause the video, write your equations, see if you got them right. All right, here's what you should get. Again, net forces are 0. Force in the direction of motion minus the forces that are opposing motion, solving for t. Same thing here, force in the direction of motion minus forces opposing motion, solve for t. Set t equal to each other, you get this. Very similar to number 3a. Go ahead and try number 5 on your own and see how you do. So here's what we should have. We should have weight 1, Fn, Fd, weight 2, tension up here, and then we have to decide where Fk is going. Is it, if it's sliding down the ramp, then friction would be up. If it's sliding up the ramp, then friction would be down, but we don't know. So we have to make an educated guess. Here's what I would look at. The weight here is going to be equal to the tension if we say that it's at rest. So if the tension pulling up is greater than Fd, what's it going to do?